Question 3. The hydrogen halides, hydrogen chloride, hydrogen bromide, and hydrogen iodide are all colorless gases at room temperature. Part A. The hydrogen halides can be formed by reacting halogens with hydrogen. Describe and explain the relative reactivity of halogens down the group when they react with hydrogen to form hydrogen chloride, hydrogen bromide, and hydrogen iodide. Of course, the reaction becomes less vigorous down the group. So the reaction is less vigorous down the group. Down the group. Why? We see that electronegativity decreases. Remember, electronegativity is the power of an atom to attract bonding electrons towards itself. So as we go down the group, we see shells which are being added, okay? When shells are being added, then that means that these these outermost electrons, or the incoming electron now, is far distant from the nucleus compared to the one that has gotten these very few. So the reactivity is actually very strong here. The reaction is so vigorous for chlorine because for it is smaller than the bromine and iodine. Okay, so that is that. So electronegativity decreases down the group. We see less attraction of electrons that are being added there. We are also seeing weaker oxidizing agents. Okay, they become stronger reducing agents and weaker oxidizing agents. So it becomes very hard for them to gain the electron, because to gain electrons, that means you are being reduced. Okay, the one that is being reduced is an oxidizing agent. Since it is hard because of the long distance here, because of the smaller nuclear attraction, then that means that they become weaker oxidizing agents. So what I can say is that this is because of the greater shielding of outer electrons, that outweighs the nuclear charge. Remember, as you go down the group, you are adding a shell of electrons, and also protons are being added to the nucleus. So the nuclear charge is there. Okay, the nuclear charge has increased, but then because of the shielding, then the nuclear attraction for this incoming electron is going to be reduced. Okay, so that outweighs the nuclear charge. Okay, hence decreasing the attraction of electrons, or nuclear attraction, okay, of the incoming electrons. So that is that. Then part B, HCl is a product of several different reactions. Some of these are shown in this figure here. So we are seeing silicon 4 chloride. When it reacts with water, we get silicon 4 oxide and then the HCl. Then we also have sodium chloride reacting with concentrated sulfuric acid to get HCl. Yes. Concentrated sulfuric acid can react with sodium halides, or the halides, to form hydrogen halides. Let's say HCl, there is HI, then HBr. Then these ones break down, okay? But this one doesn't. That one is also very examinable. Okay, let's continue. Now they are saying write an equation for reaction 1. Here we have silicon 4 chloride plus water. Then you get silicon 4 oxide plus HCl To balance this, since chlorines are 4 here, I will put a 4. Okay? Then oxygens are 2 here, I will put a 2 here. Then even hydrogen will be 4 and 4. So that is that. Roman 2. In reaction 2, sodium chloride reacts with concentrated sulfuric acid to form HCl and sodium hydrogen sulfate. Yeah, sulfuric acid here has lost a proton because now you are seeing hydrogens, now 1. That's what we call an acid-base reaction. Okay? Then, when sodium bromide reacts with concentrated sulfuric acid, the products include bromine and sulfur dioxide. So the sodium bromide, okay, I mean the hydrogen bromide, which would have been formed here, is broken further. Because as you go down the group, I said these ones become more of reducing agents, and sulfuric acid is a stronger oxidizing agent. So therefore, what is going to happen is the reducing agent here is going to react with the oxidizing agent. So this one will be broken further. That's why you are seeing this and this one here. Another compound is water. Okay, the same for iodine. But iodine, for which it has 3 equations. Identify the types of reaction that occur in each case by completing the table 3.1. Explain the difference in these reactions. Sodium chloride plus concentrated sulfuric acid. The types of reaction here, we only have acid-base. Acid-base reaction. Acid-base reaction. We have sodium chloride plus sulfuric acid, then you get sodium hydrogen sulfate, then plus the HCl. Okay, now this one is not broken any further, but when we have sodium bromide, this sodium bromide reacts with sulfuric acid. It also gives us first this acid-base reaction, sodium hydrogen sulfate, but then plus hydrogen bromide. Now this hydrogen bromide is broken further by sulfuric acid. So this one will give us bromine, sulfur dioxide, and water. Okay, that is what we get there. So if I put a 2 here, then I would have balanced everything. If I put a 2 here, hydrogen 2, that is 4, then 4 here, yeah, balanced, like that. So that's what we get there. Now here, this is an acid-base reaction, so I'll put it there, okay? Acid-base reaction. Then the other one is now redox reaction. This one is an oxidizing agent, this one is a reducing agent. First of all, by the way, this one is -1 here, the oxidation state of bromine. But then when you come to this one here, the oxidation state is meaning it increased by 1. So the increment in the oxidation state just signifies what? Oxidation. Then this here for sulfuric acid, the oxidation state of sulfur is +6. But the oxidation state of sulfur here is 4. So this is reduction. You see that? So it is a redox reaction. So that is that. The explanation I'm going to put here, I will say that sulfuric acid is strong enough to oxidize bromide ions to bromine. Okay, or I can say the oxidizing power of halides decreases down the group. So that is that. Then next, they are saying when heated with a Bunsen burner, HCl does not decompose, whereas these ones decompose. Explain the differences in the effect of heating HCl and hydrogen iodide. So this bond here, the HCl bond here, is stronger, okay, is stronger than that one of hydrogen iodide, okay. So why? Bond energy decreases down the group, Now, why is it decreasing down the group? Chlorine, remember, is small, so with hydrogen here, but then iodine is very big, so with hydrogen here. Now the distance between the nuclei here, this nucleus here, and the bonding electrons here, it is not the same as for chlorine here, okay? So this one, the longer the bond, the weaker it is. The shorter the bond, the stronger it is. So that's why this one has gotten a stronger bond compared to this one here. So that is that. Part D, the hydrogen halides dissolve in water to form strong Bronsted-Lowry acids. The concentration of the strong acid can be determined by titration. State what is meant by strong Bronsted-Lowry acid. Now this one must be having 2 marks, yes. So you need to talk about strong and then this acid here. So an acid is a proton donor, but then the strong one is the one that fully ionizes in solution or dissociates in solution. So I will say this is a proton donor. I would have talked about the Bronsted-Lowry acid. Then let's go to the strong, that fully dissociates, okay, dissociates in aqueous solution or in water, okay, as simple as that. Roman 2, on figure 3.2, sketch the pH titration curves produced when we have 0.1 molar sodium hydroxide. This one is a strong alkali, and we also have 0.1 molar ammonia. This one is a weak alkali. They are all added to 25 cubic centimeters of HBr to excess. Now, what happens is that, let me even write something small here, okay? Sodium hydroxide is a strong alkali, okay? And then ammonium solution, it is like ammonium hydroxide, okay, is a weak alkali. Now, when we are adding these ones here, so we are starting with HBr, which is acidic, okay? HBr is acidic. So in solution, it is going to give us the hydrogen ions and then the bromide ions. So because of the presence of hydrogen ions, we are seeing the pH, which is far less than 100, okay? I mean, far less than 7. So 7 can be here. And also here, let me put the 7. Now, when these ones are reacting, because the first one here, sodium hydroxide, we are getting a strong acid, okay? This is a strong acid and a strong base. So that means the equivalence point, the neutralization point, is going to be at exactly 7, okay? So that is when, look at the molarity here. This is 0.1, 0.1, added to 25 cubic centimeters of this. So that means when we also add 25 cubic centimeters of this, remember when they react, it is 1:1. Okay, the mole ratio is 1:1. So I will also look at this 25 here. So I will draw a line here. And then another one, the pH 7 here. So the equivalence point has to be here at 7. Because we are seeing strong acid reacting with a strong base. So let me make these ones dotted, just like that. And then when I'm drawing this graph here, I'm going to start from here, like below 2, because this is a strong acid because of the hydrogen ions present. So this one will come like this. As you are adding the sodium hydroxide, the hydroxide ions will be removing the OH, I mean the hydrogen ions to form water. You see that? So this one is going to be rising. So it rises up like that, and then here it balances. So when you are drawing this line, this one, the equivalence point has to be in the middle of this one here. So when the volume is now this 25, that means the reaction is complete. Okay, when the reaction is complete, then and you add, there is going to be a sharp increase in the so that's why we are having this line here, a sharp increase in the pH, the rise in the pH. And then since sodium hydroxide is a strong alkali, the pH curve will head to the values that are greater than or equal to 12. Okay, so it will curve off like this because it is a strong alkali. Okay, from 12 and above. Okay, so that's why I'm drawing it like this, from 12 and above. Okay, so that is that. Then I can actually take off this one here, this one here. Let me just make it dotted. So just like that will be the curve. Okay, so I said here, let me just add on something. Since sodium hydroxide is a strong alkali, the pH curve, okay, the pH curve heads to the pH greater or equal to 12. Okay, that end there. And also, since ammonium hydroxide, or the aqueous solution of ammonia, is a weak alkali, the pH curve heads where? Heads to, because this is a weak alkali, so you have from 8 to like 12 there. 8 to 12 or 11. I can even just put 11. Even 10, by the way. 10 there. Because from like 10 to 12, that one can be moderate. Okay? And then strong alkali, it will go up to the 14. So I will also do the same here. I'm going to draw a line here at 25. Now for ammonia here, you have, remember we have HBr here, aqueous, which dissociates completely. So we have this one here, and then the bromide ions. Then we have ammonia. I can write it like this. Aqueous ammonia is ammonium hydroxide. So this one is a weak alkali. So we can have something like this. Then ammonium ions here, then plus the OH ions here. Now, when we are adding this one here, we are adding a smaller concentration of this, okay? A smaller concentration. So by the time you add 25 cubic centimeters, like the same volume, then there are still more hydrogen ions because of this one. So the equivalence point is going to appear below 7 because of more hydrogen ions. Do you get what I'm saying? But then here, for this one, as you are adding, the hydrogen ions are taken away by the OH ions. So here we are having there is a high concentration of sodium hydroxide, a high concentration of hydroxide ions, so which will take out the hydrogen ions. In fact, let me just also write the same thing here to make the point go home. Now remember, here we have sodium hydroxide. So this is sodium hydroxide, which is a strong alkali. So we have sodium ions here and that. Now what is going to happen is that when you are releasing sodium ions, I mean hydroxide ions in here, these ones will automatically take off this. So by the time you equate the volume here, even all the hydrogen ions have been depleted. But here, by the time you come to 25 cubic centimeters, because you are releasing a very low concentration of hydroxyl ions in here, and this one is fully dissociated, you are going to remain with some more hydrogen ions in here. Okay, so that means the equivalence point is going to happen at a pH which is below 7. Okay, below 7. I can even put it around here at 6. Okay, around 6 here. So I will draw my line maybe below 6 or just at 6 there. So like that. Then we draw just like the first one here. It is below the 2 because it is a strong acid. So this one will come like this. Remember, this equivalence point here has to be in the middle. It balances. Now, this one here is a weak alkali. So the moment I come to the equivalence point and then we add more OH, then the pH is going to shoot. Okay, just like I explained here. So it shoots, but then it is going to head off from 8 here. It will not go beyond. It will not go up to like 12 there or above. Why? Because this one is a weak base. So its pH is going to be just above there. So I'm going to have this one I put off. Let me make this one dotted and also this one here dotted. So that is what we are having there. Okay. But let me take off this one here and the same thing here. So those are our curves we are going to have there. Part E, hydrogen bromide reacts with propene to form 2 bromoalkanes, the primary one and then the secondary one. And then they are saying that complete the diagram to show the mechanism of the reaction of hydrogen bromide and propene to form the major product. Include charges, dipoles, lone pairs of electrons, and carry arrows as appropriate. Draw the structure of the intermediate and the major organic product. Okay, now there is a major and then a minor because of the stability of the couple cations. Now, since these two here have different electronegativities, bromine here is more electronegative compared to hydrogen. So it will tend to pull bonding electrons towards itself. Therefore, it is going to attain a partial negative charge. And then hydrogen here will attain a partial positive charge because it will appear to have lost the electrons to bromine. And now, this pi system here has gotten electrons. So therefore, because of this partial positive charge here, then the electrons can easily flow from this pi system to this hydrogen here, which appears to have lost electrons, and then this one heterolytically breaks down. Okay, so when it does so, now we are going to have this one here is the CH3. So I'm going to have, I can write CH3 here, then connected to this carbon here. Now, what happens is that I always said the rich get richer. So the carbon, which has more hydrogen atoms, will get a hydrogen atom, okay, first. Now, when it gets that hydrogen atom first, we are going to see a CH3 here. Now, these are two alkyl groups here, and they have the positive inductive effect, okay? So they tend to push electrons towards this carbon here, okay? This carbon here, you see that the carbocation, and then in that sense this one becomes much more stable compared to when you have the CH3, then C, and then this one gets the hydrogen first, then they become 2, and then CH2 plus. So this one has one alkyl group, so whose inductive effect is smaller than for these two that are here. Okay, so that's why this one is minor and this is the major. I hope I'm clear there. So now let me come back to this one here. So I'll remove those arrows, and then the bromine, this one must have a plus, okay? Then bromine here, it's minus because it received electrons here. And then it has a lone pair, then that lone pair can give to this one, which appears to have lost electrons. Okay, that is now, the intermediate is this one here, without this one. Okay, so that is that. And then the product we are going to get is this CH3, C, then CH3, CH, and then the Br. So this one here, so that is that. Roman, to explain why the two bromoalkanes are not produced in equal amounts by this reaction. Okay, that's exactly what I've been talking about. We have seen that this one is a secondary carbocation, okay, which is more stable than the primary carbocation. So I will say secondary carbocation, secondary carbocation is more stable, than the primary I think I can just I don't need to write again carbocation. Okay, why? Because greater positive inductive effect of two methyl groups. So that is that. Or you can even say the primary carbocation is less stable compared to the secondary carbocation. And then you talk about this one here having one carbocation. Okay? I mean the primary carbocation. It is formed from the primary carbocation, and this one is formed from the secondary carbocation. So whatever. But you have to talk about the stability of the carbocation and then which one has a greater positive inductive effect. So stability of the carbocation and then the inductive effect. Those are the 2 points that must appear in your answer. Roman 3, the reaction of this bromopropane and sodium hydroxide is different depending on whether water or ethanol is a solvent. Yeah, if it is sodium hydroxide here, aqueous, or water being the solvent, that means you're going to form an alcohol. But if ethanol is the one that is the solvent, then this one is going to be an elimination reaction. You are going to form an alkene. So complete table 2 to identify the organic and the inorganic products of reaction for this one here and sodium hydroxide in each solvent. Okay. Now, we are going to have the organic product with water. Remove this and put OH. So here I'll put CH3, CH2, CH2, OH. The inorganic product, of course, has to be sodium bromide. Okay? If this one is substituted with this, then these two will form sodium bromide. And then when we put ethanol, ethanol as a solvent, what happens is that you are having CH3, CH2, then CH2Br. So this one is going to lose the Br, then this one will lose one hydrogen, then we create a double bond here. So that one will give us what we call a propene. So we shall have CH3, CH, double bond, CH2. And then from here, we have removed HBr from there. Okay? We have removed HBr from there. So I can write water and sodium bromide. Okay? I would have put, what do we have here? HBr. Okay, HBr here. But since I have sodium hydroxide, okay, since I have sodium hydroxide there, then we shall get water. This is an acid-base reaction. So you will get sodium bromide and then the water. So that's why here the inorganic product, instead of putting HBr, we put these two. I hope that is clear. Okay. So in fact, let me write this one here. HBr plus sodium hydroxide. Then we shall get sodium bromide plus water, like that.